Divisibility. An integer a is called even if there is another integer b such that a is equal to 2 times b. Let's look at some examples. 6 is even because 6 is equal to 2 times the integer 3. Negative 14 is even because negative 14 is equal to 2 times the integer negative 7. 1 can be written as 2 times 1/2, but this does not show that 1 is even. In the definition of even, it is very important that b is an integer. 1/2 is not an integer, and so it cannot be used as a value for b in the definition of even. If a and b are integers, the sum of a and b is a plus b, and the product of a and b is a times b. Theorem. The sum of two even integers is even. Before we write out a full proof of this theorem, let's come up with a strategy. We will start with two arbitrary but specific even integers. Let's call them m and n. Notice that we need to give them different names because there's no reason that they need to have the same value. When we try to add m and n, we get m plus n. Why should m plus n represent an even integer? Well, we first invoke the definition of even. We get integers j and k such that m is equal to 2j and n is equal to 2k. Now, when we add m and n, we get m plus n is equal to 2j plus 2k. That's by direct substitution. Is it clear that 2j plus 2k represents an even integer? Nope, not quite yet. To be even, our final expression needs to have the form 2b, where b is an integer. Here is where we use the fact that the set of integers, together with addition and multiplication, is a ring. Specifically, we use the distributive property to rewrite 2j plus 2k as 2 times j plus k. It looks like we've done it. But we just need to verify one more thing. Is j plus k an integer? Once again, we use the fact that the set of integers together with addition and multiplication is a ring to verify this. Specifically, we use the fact that plus is a binary operation on the set of integers. So in other words, when we add two integers, we always get an integer. That will guarantee that j plus k is an integer. Okay, let's go ahead and write out the proof in detail. Our opening statement is let m and n be even integers. Now we use the definition of even. Then there are integers j and k such that m is equal to 2j and n is equal to 2k. So m plus n is 2j plus 2k by direct substitution, which is equal to 2 times j plus k, because multiplication is distributive over addition in the set of integers. Since the set of integers is closed under addition, j plus k is an integer. Therefore, m plus n is even. An integer a is divisible by an integer k if there is another integer b such that a is equal to k times b. We use this symbol, a vertical line between k and a, to indicate divisibility. To indicate that a is divisible by k, we usually read this as k divides a. Okay, and a few ways to say this. We also say that k is a factor of a, k is a divisor of a. As I've said, k divides a, or a is a multiple of k. These all mean the same thing. Let's look at some examples. First, it's worth noting that being divisible by 2 is the same as being even. So this definition of divisibility generalizes the notion of even to other positive integers. 18 is divisible by 3 because 18 is 3 times the integer 6. Negative 56 is divisible by 7 because negative 56 is 7 times negative 8. Another theorem. The product of two integers that are each divisible by k is also divisible by k. Okay, the proof is very similar to the proof of the last theorem that we did. So let's go through it. Let m and n be integers that are divisible by k. Then there are integers b and c such that m is equal to k times b and n is equal to k times c. So m times n is equal to k times b times k times c, which is equal to k times b times k times c, because multiplication is associative in z. If you're not quite seeing that clearly, don't worry. We'll clarify that in just a moment. Since z is closed onto multiplication, b times k times c is an integer. Thus, m times n is divisible by k. Okay, and that's the end of the argument. Now, I promised a clarification of this step here, just in case you're not quite seeing how we used associativity to regroup those parentheses. We can see this a little more clearly by first making a substitution and letting u equal k times c. So we have k times b times k times c. Replacing k times c with u gives us k times b times u. And now we can use associativity to regroup those parentheses and write this as k times b times u. And finally, we can replace u by k times c, remembering to keep that expression in parentheses, to get the end result that we were looking for.